Welcome back. So here comes the finite element method. We want to start from the very basic, based on the problem statement, the governing equation that was derived in the previous lecture. So if you missed the governing equation, you can just go back to the previous lecture and just see which problem I'm going to solve. Right, so in the previous lecture, we introduced the strong form, but in order to solve with finite element method, we actually need another approach, which is called weak form, or the principle of minimum potential energy. So unlike the strong form, where the second order differentiable solution field is required, the weak form only requires first order differentiability to the solution field. That's why it is called weak form. And to derive this weak form, we use the principle of minimum potential energy. So by definition, the deformed state a structure attains upon the application of forces is the equilibrium state of a structure system, or the state where the potential energy of the system is minimized. So what is the potential energy? This potential energy of a system is defined as strain energy minus work done by the external force. So let's go back to our problem statement. This was our problem, right? And mathematically, we can define the strain energy and work done by the external force as this. Especially the strain energy is expressed as an integration over the domain, and this was strain, right? So square root of the strain times Young's modulus and area, right? So if you plug this in, you can formulate your principle of minimum potential energy, or the potential energy pi, as this. And you want to find out the solution field ux, is just function, that actually minimizes this potential energy. So that's it. This is an alternative way of solving the same problem through the weak form, or the principle of minimum potential energy. All right, now we want to introduce the finite element method. So you can see the diagram here. We actually divided the entire 1D body into 4 different elements, non-overlapping, right? And each element has node, right? We have node 1 through node 5. The reason why we do this kind of discretization is that most partial differential equations are not solvable with hand. So that's why we divided this into multiple non-overlapping elements. We kind of approximately solve this PDE through the FEM. So in FEM, we divide the domain into elements. We have 4 elements, and each element is defined as nodes, right? So each node has its coordinate and nodal displacement field, or nodal variable. Okay, nodal values. Then we want to interpolate, this is very important, we want to interpolate the nodal displacement ui with known analytical functions like polynomials, or whatever you want. The easiest and most widely used approach is the linear interpolation, because it is easy to implement and computation speed is fast. So we want to say p equals 1, which is the polynomial order, denoting the linear interpolation. All right, let's go step by step. So assume that we have a random set of nodal displacement ui, like this. So finally, what we want to do is we want to interpolate those nodal values through a linear functions. So this is going to be our approximate solution field. Of course, we want to optimize this u1 through u5 through the principle of minimum potential energy. So mathematically, we can write the linearly interpolated function uh, which is shown here, as this, right? This piecewise linear function, there are 4 functions because we have 4 elements, is defined like this. This is very simple linear interpolation, right? But it is easier to formulate the problem by element. That's why it is called finite element. So we call this UH of E, meaning the interpolated field of element E is this. So we just pick one of this out, right, and replace the index with element index E. So when we plug this in to the principle of minimum potential energy, this potential energy, you will see now this. This is going to be our potential energy defined on the 4 segmented domain, where we have nodal displacement U1 through U5. Okay. Now the integration of the entire domain is divided into 4 summations of 4 integration, all for each element, right? So after doing a simple, hand calculations, this is 1D functions, you will get a potential energy as a function of nodal displacements, U1 through U5, like this. So the first term, the strain energy, is a function of the second order of the nodal displacement, and the second term is the first order, right? Now we want to find out the minimum of this potential, right? Subjected to U1 equals 0. Remember, U1 was 0 because the left-hand side was fixed, right? Okay. Since it's an optimization problem, there's an optimality condition, right? So this is our optimality condition. Now it becomes a simple system of linear equations where U1 is 0. So we can solve it very easily, right? And this is our solution. So U1 through U5. And if we plot this, this is our finite element solution. So you can see here, the exact solution was a smooth field, but now our finite element solution is piecewise linear with 4 segments. And if you look at the stress, which is a first order derivative of the displacement field, you can see here they are stepwise. It is quite obvious. And there's an error. For this error, I collect the H1 norm error. I can see this paper if you want to see in details. But the error value was 1.0597 10 to the minus 1. All right, so let's go back to the program that I shared with you and see how this program is coded. All right, if you click this Colette notebook file or Jupyter notebook file, you will see this one. So basically, this code has FEM, hidden FEM, and C-HiDeNN for the same problem. And also, remember, this code is written in JAX library that automatically supports the GPU computation. So actually, I don't want to go into very detail in this code, but I just want to show you how to run this code. So for step by step, I'll introduce each block. So the first block is the library importation, right? So you can import libraries. And pre-processing for the first block is a Gaussian quadrature, the numerical integration rules, right? And there's a mesh generator. Of course, we have to generate the mesh. And here's the Gauss quadrature rule, actually where the numerical integration takes place. And here's a function of function block of finite element method. So this is a standard finite element. Remember, this is not that long compared to the standard MATLAB-based, CPU-based finite element code, because we're going to leverage the parallel capability of JAX. Okay, let's skip this part. And also there's a hidden FEM functions defined and convolution hidden functions defined. So going all the way down, at the end of this block, you will see this main program, where actually you change only this block, only this part. Actually, I only want you to change this 3 lines, run FEM, run hidden, and run C-HiDeNN. So I want to set, since this is a finite element tutorial, I want to set this as false. And I will run everything. So I will only run finite element and compare with the exact solution. All right? So I'm going to run all. It may take some time, but it's not going to be that long. All right, here comes the result. You can see exactly the same plus that is shown in the slides. All right? Remember, we start with a uniformly spaced elements. So now that's why the spaces are uniform. You can also select the uniformity of the element at this boolean. You can set the uniform mesh bool as false, because this means you're going to do the uniform mesh. If you set this as a true, then it's going to be a non-uniform spaced mesh. All right, that's it for this tutorial, and I hope you see you in the next tutorial. Thank you.